This is Food Science 571, Food Process Engineering Technology. This is your instructor, Dr. Baird Vaughn, of the Department of Food and Nutritional Sciences. We are starting with Topic 2, Physical Properties, Lecture 3 of 4. As we continue with physical properties, there's a need for an understanding on solid-fluid behavior. Rheology is the science devoted to the study of deformation and flow. Any material can be a solid, liquid, or gas. However, fluids are only gases and liquids. Food is usually a mixture, liquid or solid. And the importance of understanding solid fluid behavior is that design of fluid handling systems, instrument and sensors for process control, the force and energy required for size reduction, the strength to withstand puncture, cracking, crushing, and loads, the tenderness of meat products, and correlating texture with sensory properties. When we talk about what a liquid is a material that's able to flow to take the shape of a container. However, a material that's a solid maintains their shape with relatively minor changes after undergoing external loads or stresses. When we're discussing stress and fluid flow, normal stress or pressure is a force acting perpendicular to a surface. However, shear stress is force acting parallel to a surface. Material classifications are several different types. Elastic is a material where, when the shear stress is applied, proportional definite deformation, no flow of material, it returns to its original shape when stress is removed. There are lots of different plastics that do this, or rubbers that do this, and certain foods. When you have a plastic or viscoelastic material classification, when shear stress is applied, it deforms continuously, the deformation is proportional, and it does not fully return to the original shape when stress is removed. An example would be Jell-O or soft cheese. When you have a fluid, when shear stress is applied, you have proportional deformation, and there's no recovery when the stress is removed. Materials that are classified as incompressible fluids, when you have no observed reduction in volume when normal stress is applied, and normally those are liquids. And when you have compressible fluids, you have a reduction in volume with application of normal stress, which is a gas. An example of understanding the difference between incompressible and compressible fluids is you can put water in a balloon, and if you squeeze it, you can't really compress it beyond a certain amount before it busts. However, a compressible fluid like air, or if you breathe into a balloon and you try to compress it, it will compress without it actually breaking. The gas itself will compress within the balloon. Here we have a schematic representation of the response of elastic, viscous, and viscoelastic bodies to the application and removal of a stress. When you see the unstressed, they're all pretty much blocks or cubes. You have the stress that's applied, and you can see in the last column, the elastic, when the stress is removed, it returns back to its original shape, which you see in the first column. A viscous material, it doesn't return at all past where it was actually stressed. However, with a viscoelastic material, you can see that it actually comes back somewhat, but never regains its original shape as shown in the first column. There are many different classifications of rheological behaviors. Different materials will act in different ways. And between two general classifications, fluids, which have a viscous behavior, and solids, which have a more elastic behavior, you have a whole range of different types of behavior that you actually find. Where this becomes important is that there are certain foods that will exhibit certain types of rheological behavior. That is to say, under certain conditions, they will act a certain way different from what other kinds of materials may act, and this can become important when you're looking at how you manipulate or process different biological materials. When we start to examine rheology, there are common rheological instruments are divided into two major categories, rotational and tube type. And what you see here in this slide are the different kinds of instruments that are actually used to investigate the different rheologies of materials. As we begin to discuss fluid flow, there are certain definitions that we have to show. A number of the shear rate equations are shown, and we'll cover an amount of this information later on in the course. But du dy is the shear rate, which is the velocity gradient normal to flow direction, and the units are inverse second. Also, sigma is the shear stress, which is the friction force per unit area. Going into a little bit more detail, density, again rho, is the weight of material occupying a unit volume. Viscosity, the dynamic viscosity, is a measure of the resistance between internal layers of a fluid to movement due to application of shear stress. It's represented by the Greek letter mu. Units of viscosity are Pascal seconds, poise, or centipoise. And the influence of temperature is shown in the equation below, which is an exponential equation. The kinematic viscosity is the ratio of viscosity to density, is represented by the Greek letter nu. A Newtonian fluid is where the viscosity is not affected by changes in velocity, which could be water, honey, fluid milk, fruit juices, are Newtonian fluids. Non-Newtonian fluids are those fluids where the viscosity changes with velocity and pressure gradients and time, which would be things such as applesauce, banana puree, etc. This chart shows the classification of non-Newtonian liquids. Within non-Newtonian liquids, you have both time-dependent and time-independent liquids. And so there are different classifications within each of those categories. And this becomes important when you're dealing with a particular liquid and you need to work the process around the type of liquid that it actually is. This is a diagram that shows the flow characteristics of certain fluids. And what you can see is that the Newtonian fluid, where mu is constant, is going straight up and down between the shear rate, which we discussed, and the shear stress. And so you have different types of fluid being in plastics, your non-Newtonian fluid, dilatant fluid, pseudoplastic fluid, and ideal fluid, which is where the shearing stress does not have anything to do or is independent of the shear rate. In this diagram, you see a shear stress, shear rate relationships for Newtonian and non-Newtonian liquids. And what you can see is that between the shear rate at the bottom and the shear stress, that the different fluids act in different sorts of fashions, which becomes important when you are dealing with these different fluids in different processes. So it's the take-home point really is that depending on what kind of biological material that you're working with, very few of them are going to act in an ideal way, but pumping them, moving them, and other sorts of processes will take different types of efforts. Here's more information giving a mathematical model for non-Newtonian fluid by the Herschel-Buckley model. The take-home point for this is that you have these different types of fluids, Herschel-Buckley, Newtonian shear, thinning, shear thickening, Bingham plastic, but on the final column you see typical examples of each of those. For example, when it comes to a shear thinning type of fluid, you have applesauce, banana puree, orange juice concentrate, and so how you handle it will have a lot to do with what type of fluid it actually is. Here we have two other diagrams. The first figure at the top shows pseudoplastic flow, with A being shear stress versus shear rate, and B being apparent viscosity versus shear rate. And so you can see that there are certain types of behavior that you have with pseudoplastic flow. At the bottom you see dilatant flow, which is shear stress versus shear rate, and the apparent viscosity versus the shear rate, which is in the second diagram. And you can see that just there are different types of behaviors for those fluids that would be classified as either of these types. When we talk about the measurement of viscosity, there are two different types of viscometers that we can use. There's the capillary tube viscometer and the rotational viscometer. And what you find in the top diagram, a capillary tube viscometer, the force balance for a section of capillary tube is shown, and that's how it is using those forces to determine what the viscosity is. In a rotational viscometer, you can see where you have a schematic illustration of a coaxial cylinder rotational viscometer, and you see that the cylinder is actually spinning, and then you'll measure the viscosity from that exercise. Here you see the shear rates typical of familiar materials and processes. So each of the different processes that you may be doing, you may be extruding, you may be calendaring, pouring from a bottle, flowing through a pipe, brushing, spraying, coating, and lubrication. They have their own shear rates. And so the applications you see on the right hand side. So for example, if you were dough sheeting, the situations that you're calendaring. When you have rubbing, you're talking about topical application of creams and lotions. Also, if you're thinking about lubrication, you're dealing with the application of bearings, gasoline engines, those kinds of things. So each of the different processes have particular shear rates that come into play with the type of material that you're actually working with. We now start the section on thermal properties. Food materials are exposed to heat transfer numerous times: heating, cooling, refrigeration, and chilling, baking, frying, freezing, pasteurization, and concentration. Thermal properties are important to the rate of heat transfer, and they're unique for each food. They're affected by composition, moisture, and temperature. There are tabulated data sources for thermal properties of foods, which are examples are shown below. The first thermal property we'll discuss is specific heat, which is represented by the letter C. Specific heat, and a variation of it, the heat capacity, is the heat required to increase 1 unit of mass by 1 degree temperature. The unit of specific heat is joules per kilogram Kelvin, or kilojoule per kilogram Kelvin. And the measurement is done by a DSC, which is a particular piece of equipment. That's the acronym for it. And the specific heat of water is 4.187 kilojoules per kilogram Kelvin. For ice, it's 2.1 kilojoules per kilogram Kelvin. And for a variety of food materials, they'll range from between 2.5 to 4.0 kilojoule per kilogram Kelvin. The specific heat above freezing is shown in terms of the mass fraction, which is X. Below freezing is also shown as well. The ASHRAE data gives it this way, and then when the food composition is known, you can calculate the specific heat by knowing the different components which are represented by X sub C, X sub P, X sub S, X sub A, and X sub N, which will be discussed shortly. Shown here are specific heat relationships for food product components. The different components are the basic ones for food: protein, carbohydrate, fat, ash, water, below and above Celsius, 0 Celsius, and ice. And you see that there are temperature relationships for all of these different components. Here is a diagram of specific heat of food products based on ASHRAE data. And so you see that there's somewhat of a linear relationship between the water content by mass and the specific heat. And at the lower end of the scale, you see foods such as dried beef and white bread. At the top of the scale, you see things such as peaches, apple juice, and asparagus. And you can see that there's a relationship between the specific heat and the water content, which is X sub W. Specific heat is also affected by the temperature and freezing. And you can see in this one example the effect of freezing on the specific heat of sweet potato puree. Thermal conductivity, represented by the letter K, is another very important thermal property. Thermal conductivity is a measure of the ability of a material to transmit heat. The rate of heat that will be conducted through a unit thickness of material if a unit temperature gradient exists across that thickness. The unit of thermal conductivity is watt per meter Kelvin. Water, food, and metals, as well as air, have different ranges of thermal conductivity. And the thermal conductivity plays into how it transfers heat. When we look at certain biological materials, meats have thermal conductivities that are shown in the range below, and it's proportional to the percentage of water that's included. Fruits and vegetables and solid and liquid foods are also shown in terms of their relationship to either their component parts or to their percentage of water. The measurement is a line heat source probe method, which will give you a measurement of the thermal conductivity of a food. Here we see thermal conductivity relationships for components of food. The components again are protein, carbohydrate, fat, ash, water, and ice. And you can see that there are temperature relationships between the thermal conductivity and the temperature. This is a diagram that shows the effect of freezing upon thermal conductivity of selected products. And you can see how the thermal conductivity actually decreases for most foods as they become closer to 0 degrees Celsius. Another important thermal property is thermal diffusivity, represented by Greek letter alpha. Thermal diffusivity is a measure of the ability of a material to conduct heat relative to its ability to store heat. And it's actually a relationship between the thermal conductivity, the density, and the specific heat as shown. Also, it's a function of moisture content, temperature, and composition. The units of thermal conductivity are meters squared per second, and typical ranges for food materials are 1 point times 10 to the minus 7 to 2 times 10 to the minus 7 meters squared per second. Measurement is often estimated from measured values of K and C, but there's also a way of measuring the thermal diffusivity given the different components as shown below. This diagram shows density relationships for food product components. And you see the different components and the temperature relationships shown as functions of temperature. Also, you see the thermal diffusivity as functions of temperature as well for the different components. Another property is the convective heat transfer coefficient, which is designated by the symbol H. It's a measure of heat transfer rate between a solid object and the surrounding fluid. It depends on the food material, including the surface characteristics of the solid and the geometry, the fluid velocity and properties. And so shown are approximate values of H for different fluids. You see the H, which has the units of watt per meter square Kelvin for gases, viscous liquids, water, liquid metals, boiling water, and condensing steam. The latent heat, which you may recognize from your chemistry course, is the heat exchanged during a change in phase without a change in temperature. The latent heat of vaporization is the amount of heat required for liquid water to go to vapor. The latent heat of fusion is the amount of energy required for liquid water to go to ice. It's interesting if you compare the amount of energy that it takes to raise the temperature of water from 0 Celsius to 100 degrees Celsius, which is 420 kilojoules, to the amount that's required to actually evaporate it at 100 degrees Celsius. The importance of the latent heat is really in certain processes such as the drying and dehydration of food products, fruits, vegetables, and grains, where the water that's in the food is being vaporized and leaving the food. It's the same with evaporation, where you have something such as a fruit juice concentrate where the water is leaving the concentrate itself. Also, you can estimate the latent heat of fusion by the water content. Also, there's freezing point depression, where you have pure water at 0 degrees Celsius. The presence of a solute or a solid reduces the freezing point. Also, you have the heat of respiration, which is heat produced by fruits and vegetables while respiring. That is transforming sugar to carbon dioxide and heat. And that's also tabulated in the appendix. What you notice is that you have an increase in the surface temperature and moisture transfer from fruits and vegetables. Another set of properties that we examine are electromagnetic properties. And these are properties that are related to the electromagnetic spectrum. What you see in the diagram below actually is the electromagnetic spectrum that goes from cosmic rays, gamma rays, X-rays, ultraviolet rays to the very limited visible spectrum that we have onto infrared, radio waves, and electric waves. This is another diagram of the electromagnetic spectrum, and what it shows is the wavelength of the different types of waves, and it shows different sizes of the wavelength, ranging from the size of a soccer field to smaller than a water molecule, and the common names of the waves range from radio waves, microwaves, infrared. You can see that the visible spectrum is very small: ultraviolet, soft X-rays, hard X-rays, and gamma rays. And you can see where the sources are, and the one that we use quite a bit in food processing would be your microwave oven, which you have microwaves, of course, and we use that to actually cook and to heat food. When we talk about the visible spectrum, those waves that we can actually pick up with the eye, we look below at the different colors and their wavelengths and frequencies. This becomes important when we have perhaps quality control for certain foods that should be in a certain color range. There are also electric properties where we talk about the conductance or resistance of materials, dielectric properties, and near infrared properties, and irradiation. And below you see a diagram that shows relationship between conductivity and the moisture content. This diagram below shows the dielectric properties of foods and materials at 2,450 megahertz. So there are different dielectric properties of food that go into how they're handled, how they can be cooked, and other sorts of properties. We won't deal very extensively with these, but it's important that you understand that different foods, depending on their composition, exhibit different properties under different situations. This is a diagram of dielectric properties of food at 20 degrees Celsius, which demonstrates the relationship between dielectric properties and moisture content. Here you have a variety of different foods at different moisture contents, and you see how the moisture content influences in certain foods the dielectric properties that you actually have. And the dielectric property goes into how it can be processed. This concludes the third lecture of Topic 2, Physical Properties. If you have any questions, please contact me at the email address given in the syllabus. Thank you.